The area of polar functions I'm going to deal with in three separate shorter videos here, just to deal with kind of three scenarios that we see with polar functions. Uh, One thing I'm not going through is it is possible to change a polar function into rectangular form and then use multiple integrals to find the area you need, because almost all polar functions we're not dealing with uh, functions in rectangular form. So the three ways I'm going through are if I leave them in polar. You're welcome to change them into rectangular and deal with it that way. Go right ahead. Just because time is an issue on the AP test, it's sometimes just faster to leave them as polar. And the idea of it is uh, to find the area inside of a polar function. It's the integral from alpha to beta, where those are the angles that theta is between, of 1 half r squared d theta. And where the 1 half r squared d theta is coming from is we're treating this like sectors of a circle. Um, and remember, the sectors of a circle, to find the area, it's 1 half r squared times the fraction of the circle you're looking at. And that's what d theta is. It's the fraction of the circle. And it's an infinitesimally small change in the angle. So we add all this up, it gives us the whole area. And r is not going to be constant because we're not really dealing with circles here. So if, for example, I was looking at finding the area here enclosed by 2 times 1 plus cosine theta, uh, really all I need to know is what r is, in which case this is given, and what theta goes between. And in polar form, I could just hit trace and trace around to see what theta is going from, to get from 0 to back to the starting position. And if I do that, I'll see that uh, at 0 it starts here, it goes around this way, and it ends up back here when theta is 2 pi. So it does follow the format that we're used to. Typically, if we're doing within an entire polar function, it's going to be 0 to 2 pi for the most part, sometimes just 0 to pi. Uh, and occasionally, if we have something nice and symmetric like a rose, we'll just do one petal uh, and then multiply by the number of petals, just to make things a little bit easier for us. Uh, so all I need then is, this would be the integral. I figured out theta goes from 0 to 2 pi of 1 half times my function, my r, make that a little sized better, squared d theta. I could go ahead and do this algebraically. If I were to do it algebraically, I would FOIL out the r squared part and then do each individual term. But doing it on the calculator is just here to save time, which I already did. And I get that my area then is 18.850, which is about 6 pi.